Okay, let's continue with the performance and operation of industrial manipulators and how these two are connected. The first thing that we need to know is that serial kinematic mechanisms are significantly more repeatable than they are accurate, which means that positioning accuracies for industrial manipulators range from 10 mm for uncalibrated manipulators to 0.1 mm for calibrated manipulators, and their positioning repeatability range from 0.2 mm for large spot welding robots to 0.005 mm or 5 micrometer for precise micro-positioning manipulators. So, what does this mean? This means essentially that a robot is much more likely to re-attain a position based on a configuration that it has been in before, than that it is going to reach this position for the first time. And let's consider this in an example, because this in itself essentially defines online and offline programming. Let's have a look at this video before we are going to discuss the most essential aspects of online and offline programming. If you want to watch those videos on your own, you find the references, or that is the link to the videos on YouTube, in the notes of the lecture slides. In online programming, you find yourself on the shop floor programming the robot by either using the teach pendant in order to store certain configurations, or you are using lead through teach programming in order to drag the robot along a trajectory and then store all the configurations along the way. And the benefit of online programming is that it is repeatability dependent rather than accuracy dependent. And as we have established on the preceding slide, the repeatability is about 10 times bigger than the accuracy of the system, which you are dependent on in offline programming. So in offline programming, you are sitting in front of your computer and defining the trajectory, being dependent on the accuracy. This is the reason why most commonly you will find that in industry, robots are being programmed as a mixture of online and offline. Because if you're doing the online programming, you know that you're going to get the highest positioning accuracy that you're aiming for, but at the same time you have to shut down the production in order to teach in the program, and also you are dependent on the individual piece of machinery itself. So you cannot just simply transfer the program from one robot to the other. As I said before, simplification is going to be a huge driver for the increased adaptation of industrial manipulators, and topics that are being developed or being researched in order to reduce the complexity associated with robot programming is to make CAD data available wherever in order to reference the CAD data to minimize the effort required by the operator, using different complementary modalities, meaning that path communication between the human and the robot can be based on speech and gesture. Also, choreographing the task movements, for instance, loops and conditions need to be researched, because as of now, you can choreograph individual trajectories, but you are missing instructions for loops and conditions. There are no instructions in order to communicate to the robot acceptable path deviations in order to be still compliant with GD&T, but at the same time maintaining a high tact in the production line. To understand where those errors come from, or where the difference in the positioning accuracy and repeatability comes from, let's consider forward and inverse kinematics. So in figure 17, you see the kinematic schema of the industrial robot that you see in figure 13. And what we need to consider is that forward and inverse kinematics is the way of calculating positions and orientations in space based on the joint angles of the robot. So we said before that an articulated manipulator has usually 6 or more degrees of freedom. The one in our example has 6 rotary degrees of freedom, θ1 to θ6. And we need to use this information in order to calculate where our end effector is going to be in space. So thinking, where is it in terms of position, x, y, and z, and in terms of its orientation, which is usually represented using Euler angles and quaternions. And in order to do that, one uses a transformation which is dependent on the Dennavit-Hartenberg parameters. And these parameters also need to accommodate errors of industrial manipulators if you want the accuracy to be very close to the repeatability. There are kinematic errors in industrial manipulators, meaning that there is a deviation in the geometry or configuration of the individual components. So you can, for example, consider that the components are not assembled together at perfect orthogonal angles, meaning 90 degrees angles, and also that there are manufacturing tolerances on the individual length of the links, so that the link is not exact 1 meter long, but within a deviation of about 50 micrometer. And those kinematic errors add up and create a difference between the positioning accuracy and the positioning repeatability. There are other errors as well, such as non-kinematic errors, which can be joint and link compliance, which describe the deformation of the components under loads. There are thermomechanical errors, which can describe the change of the kinematic parameters as a result of the change of temperature of the system, which is depicted in figure 17. And there are more errors, such as controller errors here with truncation, for example, in the case of the transformation from the joint space to the Cartesian space. Then there's wear, which can just come from the adequate or inadequate operation over time, meaning that the before named characteristics degrade, or simply coming from installation errors, meaning that you have installed your robot on a fundament which in itself is less stiff than the industrial manipulator and leads to a part of its movement. And to accommodate all or part of those errors, manipulator calibration is being used, which we can see, for example, in use in video 8. So this is an example of a robot that is being used in research in a machining application. And here you can see how the kinematics of the robots are getting calibrated. Well, actually, they're getting measured using a laser tracker. Then you are using a ball bar in order to compensate for circularity. Also, they have installed additional encoders on each axis in order to account for the deformation on the driven and the driving side. And then they use all of this information in order to increase the accuracy or getting it closer to the repeatability. And how is this being done? Well, this in itself is the topic of manipulator calibration or robot calibration, which is the process of defining an applicable mathematical model and then identifying the different model parameters such that the model describes the actual robot as good as possible. So for that, the robot calibration procedure consists of 4 steps. The first step is the modeling, and the kinematic modeling can be considered what I showed you before in the forward and inverse kinematics, where you use the information, the geometric information about the links, let's say the length of the individual length, in order to accommodate for errors in the structure. Then you're going to measure it. You have seen several measurement procedures in the preceding video where they have used a laser tracker or a ball bar. And then from this set of measurement data, you identify your new model parameters that you're then going to introduce into your model into the implementation phase in order to increase the accuracy. And there are several examples of, for example, kinematic calibration or compliance calibration or the calibration of thermoelasticity of the system. And this is just one example where you can see that the positioning accuracy before and after calibration in terms of their mean and maximum values having been conducted by researchers. And calibration is also being performed by the suppliers of industrial robots. You can find them under different names. Fanuc, for example, offers kinematic calibration under the name of IR signature, or ABB offers calibration under the name of absolute accuracy. And usually then those companies guarantee you that the mean positioning accuracy will fall of somewhere around 500 micrometers, that is to say half a millimeter, while the maximum error will be kept less than 1 millimeter. And this is useful because then if you have increased your accuracy to the level of repeatability, you can rely more on offline programming on the computer, while at the same time creating transferable task programs so that you're not dependent on adapting the task programs on the individual manipulators. If you're interested in the fundamentals of robotics, then besides the references that are given on the individual slides, I would recommend you to consult the following literature, online courses, and YouTube videos concerning the topic.